Okay, so I will first start with a brief motivation why we are interested in artificial semiconductor graphene. Then I will tell you, remind you about the magnetic properties of graphene based on Leib's theorem. Then I'm going to focus on artificial graphene, and I will discuss first the single particle results, then quantum Monte Carlo results, and I will show you our main results, metal insulator transitions. Okay, so I think we all know, and we have seen in the previous talk, that graphene, the real graphene, has extraordinary properties. We have direct fermions, very good thermal, mechanical, and transport properties. However, from nanotechnology point of view, it will be very nice if we can control engineering the geometry, size, and edge type of these of graphene, so that we can control the magnetic properties and other properties as well. So this can be done. It is very, very difficult, but however, there is still lots of work to do, because the theoretical predictions, most of the theoretical predictions are not yet observed, like magnetic properties, for instance. Or alternatively, we can fabricate artificial graphene. For instance, here using semiconductor heterostructures. There are also other ways based on optical construction or molecular ways of doing it. Here I'm going to focus on this semiconductor way of doing it, and this was recently done by Shang Wang and collaborators. They constructed nano pillars like this, and they constructed a honeycomb lattice out of these pillars, which will distort the electrons in the quantum well, the potential felt by the electrons in the quantum well, and they observed the Dirac cone, so it behaves really like graphene. Okay, so this is very nice, because there are lots of tunable parameters: the dot-to-dot distance, the radius of the dot, the potential depth in these circular quantum wells. So, which is not possible with the real graphene, where you have many uncontrolled parameters, substrate effects, oscillation problems, and so on. And this also, that would be very good for building a quantum simulator, or for instance Hubbard model, and so on. Okay, so I told you a few times about magnetic properties of graphene. Let me explain this a little bit more. Is graphene magnetic? Before talking about artificial graphene, the short answer is no. If you do the calculation, for instance, using some mean field theory, for realistic values of the Hubbard parameter U, which is lower than 5 electron volt for real graphene, so there is no magnetization in graphene, except that it was predicted in 2007 that if you have some atomic defects, such as vacancies or add atoms in graphene, there will be a magnetization induced around the defect, atomic defect. And this was recently, a few years ago, confirmed by experiments using hydrogen add atoms and also using vacancies. Okay, so there's magnetization around defects. Why does that happen? And I think the easiest way of explaining this, or cleanest way, is using Leib's theorem, discussing Leib's theorem on magnetization for bipartite lattices. And that says that bipartite lattices with Hubbard interactions as ground state that is equal to the difference between number of A sublattice atoms and B sublattice atoms. Okay. For instance, if you have such a bipartite lattice, a number of A and B atoms are equal to each other, which means the total spin should be 0. However, if you remove one of the atoms, for instance, and you have a vacancy, in that case, the total spin will be 1/2, so there's magnetization induced around the vacancy. And even more interesting, let's say you have a graphene sheet and you cut through the sheet along this zigzag direction so that all these black atoms lose their red partners. This will break the sublattice symmetry, and the difference between A and B atoms, the number will be very, very large. So you will have a magnetic edge here. You can also do the same thing here. This time the red atoms will get magnetized, but it's on the different sublattice. So there will be anti-ferromagnetic coupling between this edge and this edge, for instance. Okay, so there is lots of work trying to confirm this experimentally. There are some results, but still not very clear, not a direct evidence of magnetization at the nanoscale. Also you can also imagine lots of other geometries. One of my favorite geometries is the triangle with the zigzag edges. This should also be the edges should be polarized like this to be confirmed. Okay, so these are not confirmed experimentally. And now let's switch to artificial graphene. As a first step, I'm going to talk about single particle properties. So we can solve the Schrödinger equation in the effective mass approximation for instance, gallium arsenide. We have a potential model with lots of tunable parameters. Rho, the radius of the well. S is the sharpness of the well. And the V0 is the depth of the well. Usually V0, we tune it so that the system is charge neutral, so that the electrons don't fly away. So maybe it's not that much of a tuning parameter, but in any case. So here are some results, some different cases. For instance, for A 50 nanometers, this is from the experimental work, to be consistent with the experimental work. And we have here rho 10 nanometers, so it is a relatively small diameter, and S 0.05, not too sharp, it's kind of smooth. Okay, in that case, near the K point, you see almost like a Dirac linear dispersion. So this is nice. If you make the rho, the diameter, much larger, what will happen is that the hopping parameter T will be modified. There will be maybe a very strong second nearest neighbor hopping and effects like that. So as you can see, the Dirac cone is distorted. Or you can also change the sharpness. S100, this is like almost a square, like potential. In that case, electrons are very strongly confined in their potential. So there is almost no hopping between the wells in this case, and you get a flat, almost a flat band structures. Again, if you increase rho, then you will get a more complex band structure. So there's lots of parameters to play with, to tune with. This is very nice. This is something you cannot do with real graphene. Okay, now let's try to do some many-body investigation. So the goal is to solve the many-body Hamiltonian with an effective mass approximation again, with this model potential here. as accurately as possible. So here I'm going to use variational Monte Carlo, continuum Monte Carlo in real space. We are also doing diffusion Monte Carlo to complete these calculations, but this is work, ongoing work. So I will focus on variational Monte Carlo results here. So the idea is to build a trial wave function, which is a product of a just rho factor and Slater determinants of up and down electrons. So this just rho factor actually is a very complicated, complex polynomial with lots of parameters, optimization parameters, more 50, 60 parameters maybe, which includes the effect of electron-electron correlations, electron dots, electron-electron dot correlations. And the Slater determinants, you can use, this is maybe almost like an art, you can use any orbitals of your choice. For instance, Hubbard, back binding, density functional theories, and so on. So it is good to try different trial wave functions and pick the best. Usually that's how it is done. And then you can do energy and variance minimization to optimize all the variational parameters in the just rho factor, also in the orbitals that we choose, using Metropolis algorithm. So when we do that, okay, so this is actually our system, model system. We have a flake of 42 sites. It's a hexagonal armchair flake. We put 21 up, 21 down electrons, consistent with Leib's theorem. And the system, the potential depth is tuned so that the system is charge neutral. And dot-to-dot distance, again, it is fixed to 50 nanometers. And here we obtain our trial wave functions from Hubbards with large, first large, then small u, on-site parameter u, to see if the system gave more like a insulator or metal. Okay. We also used tight binding and localized Gaussian orbitals just to check that things were working fine. Okay. But the most important is these Hubbard trial wave functions. And here is the actually the most important results. Here is the total energy of the system as a function of rho. Rho again is the diameter of the dot. Okay, and this shows that there is a so the different colors are different trial wave functions. We have a phase transition around 20 nanometers. Okay, below 20 nanometers, the best results we get it from the Hubbard with large U. Okay, so lower energy means better trial wave function, variational principle. So, but at high rho, now it's the Hubbard with small u that becomes, that gives the best trial wave function. So, these are the spin densities that we get from Monte Carlo results. Here, clearly, we have a antiferromagnetic insulator, and around for above the critical point, we have this is almost like a noise. The energy, the scale here is much smaller than the scale here. So basically, there is no magnetic structure. Okay, almost done. We can also check the variance, and it is consistent with the energy minimization, variance minimization or energy minimization. Not that much important here. And we also, these results were for a smooth potential. We also checked the what happens for a very sharp potential, and actually we get similar behavior. Again, around 20 or maybe 25 nanometers of diameter. Below that we have a antiferromagnetic insulator, and above that we get metallic behavior. And yeah, so this is the end of my talk. To conclude, we have seen that artificial graphene enables us to tune system parameters, which is not possible with real graphene. And we observed the insulator metal transition in our variational quantum Monte Carlo results as a function of the site diameter. And this is ongoing research, so we are also doing some diffusion Monte Carlo calculations to improve the VMC results. And we also we are looking at the effects of geometry, edge type in triangular systems, and also for defects. And to finish, I would like to thank my students, PhD students, Gürkan and Bulut, master students Emre and Ismail, and undergrad student Reyhan. And thank you for attention.
Thank you for interesting talk. Can you return back to the picture? Yes, with graphene ribbons and arrows, which corresponds to magnetization of boundaries, opposite boundaries. Well, here. As for this picture is related to Hubbard model with half-fill and bend, yes, because you are using a Lieb theorem for Hubbard model with half-fill and bend for positive for repulsion with a finite repulsion. Yes.
So, sorry, I couldn't hear well. Okay. Maybe you can just repeat.
Here, this picture, yes, is related to Hubbard model with repulsion, yes, and
Hubbard model, you said?
With repulsion,
okay.
Hubbard energy, positive, yes, and with each carbon atom gives one electron to the common system. Right. This means half-filled band.
Right.
That, okay?
That's right.
But Hubbard model is hologram-Hamiltonian. Therefore, what does it mean, your arrow? Because according to some kind of theorem from quantum theory of angular momentum, yes, spin density on the edges should be 0 because ground state is has singlet. If it's singlet, spin density should be precisely 0. So in this case, you cannot put arrow here. Maybe you can say about spin-spin correlator and ferromagnetic edges in this sense, but not such kind of error. What you can say about it?
Well, actually,
any DFT calculations.
If you look at the pair correlations, spin
correlations are ferromagnetic. It's also it's theorem.
You fix one down electron here, then all these electrons will be down, all these electrons will be up. So there is antiferromagnetic.
Because of what?
Because of the
no, this arrow should be 0. This arrow should spin density are precisely 0. It's Wigner-Eckert theorem, and no contradiction. No, only if you have modified edge state, modified boundaries, you have, in this case, you have such kind of picture. And people in physical review, some people publish corresponding paper. They use density matrix method, yes, to calculate spin density distribution at the edge of graphene and obtain 0. But after that, they say experimentally said about edge state. Therefore, probably because of small energy gap, we have mixture of triplet state and so on. In this case, we have such kind of orientation, but it has no relation, direct relation to antiferromagnetic behavior of the system.
I don't think I agree. So again, if you look at the spin-dependent pair correlation functions, that actually
spin correlation function, something else.
We have done by solving many body. We have done that calculation for.
When you use average, yes, Hartree-Fock approximation.
Sorry.
When you use second line, yes, during the using of Hartree-Fock approximation. No. I solved this exactly. This was just how you can solve it exactly. It's not exactly solvable model for
for the H states. I can show you my paper where we solve this within the
exact solution of many body problem. There is only one solution for line chain.
Reduced matrix for H states.
But it's approximate. It's approximate consideration. Maybe it's approximate consideration because other atoms also affect on this H states.
Okay, maybe I'll.
Okay.
I'll
Yes,
give
I
you
think
my
we can
paper
have
where
this
we
discussion
prove
now
that.
because we are out of time. Yes, we can continue discussion because we are out of time and then we have an so thank you very much. I must give you this.